Hello everyone to the first section in chapter 5, which surprisingly starts with section 4.8. We're going to start talking about antiderivatives. Now I know this is really the last section in chapter 4, but the material that we cover in this section really goes with chapter 5, so I'm going to include this with the chapter 5 stuff. Okay? Antiderivatives and differential equations. Well, what's an antiderivative? It's exactly what they sound like. They're the opposite of a derivative. Just like addition has subtraction, division has multiplication, square root has squared, log has exponential, derivatives have an inverse. They're called an antiderivative. They have a specific name. They're really called the integral. The integral is the name of the inverse. The inverse of a derivative is an integral. The antiderivative is the process that we use. We'll go into more detail in that in chapter 5. That's really what chapter 5 is about, is integrals. For now, I just need you to be able to find the antiderivative of a function. So today, we're just going to work on the mechanics of an antiderivative and not what they mean. Okay? So let's start off with some easy ones. If I told you that y prime is equal to 1, and I want to know what function has a derivative of 1. Well, what function has a derivative of 1? X. Because what's the derivative of x? It's just 1. Ooh, how about x? Well, I know it's going to have to be x squared because the rule says subtract 1 from that. So to have an x to the first power as a derivative, I need an x squared to begin with. But if I took the derivative of this guy, this would be 2x. And that's not what I want just plain x. So I need to find some way to cancel out the 2. Well, what could I put in front that would cancel out and multiply by 2? How about a multiply by 1/2? Now if you do the derivative of this function, the 2 and the 1/2 would cancel, and it'd just be 1, and the squared would go down to a first power. And that's what I need. Let's use that same logic for this. Well, what power of x do I need so that when I take a derivative of it, I get x squared? X cubed, because if I do a derivative of x cubed, I would get x squared. But the derivative of this is 3x squared. So what has to go in front to cancel out the 3? A 1/3. You see in the pattern? Let's use a general rule. This is the power rule for integrals. Just like there's a power rule for derivatives, there's a power rule for integrals. What is the antiderivative of x to the n? It's x to the n plus 1. But I've got to balance that out by putting a 1 over n plus 1 in front. That's the general rule that we use. That's the power rule for integrals. So this is the power rule for integrals. You'll get very good at that in the next couple weeks. Okay? Power rule for integrals. Let's practice that. How about this? Well, let's rewrite the problem. I always like it as x to some power. Let's follow the power rule. The power rule says add 1 to the power. So if I add 1 to 1/2, I get 3/2. And then flip it and put it in front. If I had 1 over 3/2, which just means what's the reciprocal of 3/2? 2/3. Okay? How about this? I don't like the way it's written, so let's rewrite this. That's x to the -3rd. Well, let's follow the power rule. The power rule says add 1. Be very careful. If you add 1 to -3, you don't get -4, you get -2. And now flip it and put it in front. Cleaning that up a little bit, you'd have the -1 on top. On bottom, you'd have 2x squared. If you ever want to check your work, this is very easy to check. Just take the derivative of this and see if you get back to this. What about this one? Well, it's a combination. This is x to the -1/2. Negative because it's on bottom, 1/2 because it's square root. Power rule for integrals says add 1. If you add 1 to negative 1/2, you get positive 1/2. Flip the power and put it in front, you get 2. Or you could write that as 2 square root of x. Either way is fine. How about this? This is kind of an interesting problem. Because if you follow your rules, you're going to get something weird. So if I add 1 to the power, I get x to the 0. And then if I flip that, I get 1 over 0. Can't do that. You can't divide by 0. So this is not the correct way to do this problem. What has a derivative of 1 over x? That's the question that I'm asking. If you remember, it's one of the special ones. It's natural log of x. That's why you have to know your derivative rules, because the antiderivative rules, the integral rules, are just the same things backwards. Just like you can't divide unless you know your multiplication tables, you can't integrate unless you know your derivative rules. So this one's not a power rule. This one's a little bit weird. It's different. And this is why. Because the power rule doesn't make sense in this situation. Let's keep going. How about a problem like this where it's two things hooked together? Well, let's rewrite this as x squared minus x to the negative 1/3 power. Power rule says treat each one separately. X to the third with a 1/3 in front for the first one, minus x to the, if you add 1 you get 2/3, and you flip that you get 3/2 in front. In this case you don't need the parentheses, but sometimes you do if you put a negative in front, so I left it there. Ooh, number 10, e to the x. What has a derivative of e to the x? Oh, sorry guys. What has a derivative of e to the x? E to the x. It's its own derivative, it's its own integral. How about 17 e to the x? What do you think the antiderivative of 17 e to the x is? 17 e to the x. How about a problem like this? This looks complicated, but it's really not. Treat each problem separately. Rewrite this as x to the 1/2 minus e to the x plus 5x to the negative 3/4 power. Rewriting the problem as powers instead of roots makes this much, much easier. So this is x to the 3/2 with the 2/3 in front minus e to the x plus, that's going to be x to the 1/4. If you flip it and put it in front, you'd have a 4, but I still have a 5 here. So my final answer is going to be 2/3 x to the 3/2 minus e to the x plus 20 x to the 1/4. There you have it. So that's power rule, that's exponential rule, that's all mixed together. Well, what else do we know? How about this one? What has a derivative of sine? Well, nothing really. Because the derivative of cosine is the closest. The derivative of cosine is negative sine. So I need to cancel out the fact that there's not a negative here. So I'll put a negative there. The derivative of negative cosine is sine. What has a derivative of cosine? Well, that one's one of the ones we memorized. It's positive sine. Why? Because the derivative of sine is cosine. What has a derivative of cosecant squared? Well, cotangent has a derivative of negative cosecant squared. But I need a positive cosecant squared, so let's put a negative there to cancel out the negative. What has a derivative of secant tangent? That's one of the 6 you had to memorize. It's just secant of x. So, know your trig derivatives. They don't go away. Okay? Wait a minute. I want you to find the derivative of each of these functions. Well, Let's do a different color here, something fun. Let's do orange. What's the derivative of x squared? It's 2x. What's the derivative of x squared plus 3? It's 2x, because the plus 3 doesn't matter for derivatives. This is 2x. The minus 5 doesn't matter. People always have trouble with this one. E to the pi is a number. What's the derivative of any number? It's 0. Look, all 4 of these problems have the same derivative because I'm just adding a constant at the end of it. All of these functions have the same derivative. So which of these 4 functions is the antiderivative of 2x? Well, that's interesting. It's kind of like square root. What's the square root of 9? Well, most people would say 3, and that's right. But is 3 the only number that can be squared to give you 9? No, negative 3 can be too. In antiderivatives, there's an infinite number of antiderivatives. Any of those could work. Those are just 4 examples, but you can see any number at the end of this could make the same derivative. To find all the antiderivatives, we need to consider the transformations. Remember, a derivative is slope. Okay? It's the slope of a graph. Well, what can we do to the graph that doesn't change the slope at any one point? Like a parabola. What can I do to a parabola to not change the slope at like this point right here? I can move it up and I can move it down. And now that point is still the same slope. So we're going to add a letter at the end of this. We're going to add a plus c. C represents all the numbers possible. Now this is really important to understand here. This is a big concept that people have trouble with. Normally C just means a number. But in this case, C means every possible number. This is all real numbers. So this is not one graph. This is an infinite number of graphs. Well, what do those infinite number of graphs look like? The parabola that's moved up or down however far you want it. So it would be an infinite number of parabolas just stacked on top of each other like cups. Okay? All antiderivatives will have a plus c with them because you have to take into account every possible answer. Remember, plus c does not stand for a number, it stands for every number. Let's talk about differential equations. Well, what's a differential equation? A differential equation starts with a derivative instead of y equals. For example, every problem we've done today is a differential equation. I started with y prime equals, or I could start with dy dx equals. They mean the same thing. They're a derivative. How do I cancel out a derivative? I take the antiderivative, or I integrate. Remember, the solution to the differential equation has a plus c, which represents every possible solution. Let me show you a little notation. What is the opposite of derivative? It's integral. This is the symbol for integrals, like a big S. These two things will cancel out. What's the derivative of the integral of y? Just like what's the square root of the squared of y? Or what's 2y divided by 2? What happens to y when you do inverses? You just get y equals. But now, according to algebra, if I do something on the left side, I have to do it on the right side. Now let's just do the antiderivative. What's the antiderivative of x squared? It's 1/3 x cubed. That's going to be, that's x squared with a 1/2 in front, but there was already a 3. Now this is not nothing. When you integrate 4, you don't get 0. When you take the derivative of 4, you get 0. If you integrate 4, you get 4x plus c. Every integral problem has a plus c at the end to represent all of the infinite number of solutions this thing can have. So this is a cubic function, some sort of squiggle, with every transformation up or down of that. Differential equations are equations that include a derivative. So for both of these are examples. This is very similar to the problem we just did. If you integrate both sides or take the antiderivative of both sides, you get y equals x cubed minus 5 halves x squared plus 6x plus c. On this side, it's a derivative. It's just a different way to write it, but it's still a derivative. So I'm still going to integrate both sides. What's the integral of f prime of x? F of x. What's the derivative of cosine? Negative sine x. What's the derivative of x to the fourth? It's 1/5 x to the fifth minus 7x plus c. Sorry, I ran out of room. So those are differential equations. Take the antiderivative or the integral on both sides. If you are given a point, though, then that's a different problem. It's no longer a differential equation, it's an initial value problem. Now what's that mean? Well, how many graphs are right here? An infinite number because of that point. But how many of those graphs go through a given point? Only one. Just like over here, this is an infinite number of graphs. But if I gave you a point, there's only one graph that goes through that point. Those are called initial value problems. How many solutions to a differential equation? It's an infinite number. Why? Because of the transformations. Up and down. Algebraically, how do we represent all the infinite transformations? We have a plus c at the end. Remember, c does not stand for a number, it stands for every possible number. And if I give you a point, we restrict our answers to only one function, which solves the differential equation through a given point. Let's take a look at that. An initial value problem. In this initial value problem, I have a derivative and I have a point. People have trouble with this. What is this point? It's 0, 2. So this is saying find the antiderivative of this that goes through that point. Well, let's find the antiderivative first. I will integrate or do the antiderivative of both sides. What's the integral of dy dx? It's y. 1/3 x cubed minus 3 halves x squared plus 4x plus c. This is an infinite number of solutions. But I don't want an infinite number of solutions. I want the one graph, the one solution that goes through that point. Well, this is an x value, and this is a y value. So let's plug in what we know. 2 equals 1/3, 0 cubed minus 3 halves. 0 squared plus 4 times 0 plus c. I did one that was easy to do algebraically. What's the only thing we don't know now? C. Good thing is cancel, cancel, cancel. C equals 2. So now let's rewrite the problem. Y equals 1/3 x cubed minus 3 halves x squared plus 4x plus, not c anymore, but 2. Now what did we do? We found the initial value problem, or we found the one graph that has this derivative and goes through this point. An infinite number of graphs have this antiderivative, but only one goes through that point, and that's the graph. Basically, an initial value problem lets you solve for c. How do we graph a differential equation? Well, that's something a little bit different. How do you graph an infinite number of graphs? It has an infinite number of graphs. They all share a characteristic. They're written as a derivative. They all have the rules about their slope. To graph a differential equation, we graph these little slopes, these tiny little lines, and we call it a slope field. So we're not going to graph an infinite number of graphs. We're basically going to graph the shape of the graphs. And I'll show you what I mean. These are very, very common on the AP test, so know what you're doing. They'll give you something that looks like this. It's a graph with a list of points. How many points are here? 9. And they'll give you a derivative, dy dx, 2x minus y in this case. First of all, let's go through and make a list of all the points. This is the point, negative 1, 1, negative 1, 0, negative 1, negative 1, 0, 1, 0, 0, 0, negative 1. And you guys can see this is 1, 1, 1, 0, 1, negative 1. So those are my 9 points. I'm going to plug these things in up here. And they're going to give me a derivative. But what does a derivative look like on a graph? It's a slope. So if I plug in negative 1, 1, I would have negative 2 minus 1, I'd have negative 3. So at the point negative 1, 1, the slope is negative 3. Well, how do I graph negative 3? It's hard to graph it exactly, but in general, there's 2 things that I care about. It's negative, so it's going down, and it's 3, so it's pretty steep. So it looks like that. How about this point? If you plug in negative 1, 0, you get a slope of negative 2. So at the point negative 1, 0, I have a slope of negative 2. It's still going down, but it's not quite as steep. How about at negative 1, negative 1? I have a slope of negative 1. That's still going down, but it's on a 45-degree angle. So these 3 slopes are all going down, but they're getting less steep. How about at the point 0, 1? If you plug in 0 and 1, you get negative 1. So 0, 1 has a slope of negative 1. 0, 0 has a slope of 0, which is a horizontal line. 0, negative 1 has a slope of positive 1. Well, look at that. It's the first positive slope we've had. 1, 1, if you plug in 1, 1, you're going to get a slope of 1. It's going to look like that. If you plug in 1, 0, you're going to get a slope of 2. If you plug in 1, negative 1, you're going to get a slope of 3. Steepest yet. This is a slope field. Based on the derivative I had and the points they gave me, I found the 9 slopes that went along with the 9 points, and I sketched them. Do these have to be exact? No, you can't get them exact. What I'm looking for, or what the AP test is looking for, is are they positive when they're supposed to be positive? Are they negative when they're supposed to be negative? Are they 0 when they're supposed to be 0? Okay, that's the general idea here. What about one like this? X over Y. Well, the points are still the same. Negative 1, 1, negative 1, 0, negative 1, negative 1. 0, 1, 0, 0, 0, negative 1. 1, 1, 1, 0, 1, negative 1. And not all the time are they going to give you the same 9 points. I am, just to make it easy. Now let's plug in these points into the derivative to get my slopes. Okay? If you plug in negative 1, 1, negative 1 over positive 1 is negative 1. So it's a slope of negative 1. How about negative 1 over 0? This is undefined. Negative 1 over 0 doesn't exist. There's 2 ways to draw this. You can simply not draw anything, or you can draw a slope that's vertical. Vertical slopes are undefined. How about negative 1, negative 1? Well, that's a slope of 1. That slope looks like this. How about 0 over 1? That's 0. How about 0 over 0? It's undefined. How about 0 over negative 1? That's still 0. You could draw a vertical line here if you want to. You don't have to. How about over here? 1, 1. Well, that's 1. How about 1 over 0? That's undefined. So that's a either no drawing or that. How about 1, negative 1? That's negative 1. So it's kind of a cool looking shape. Okay? Slope fields. And that does it for section 4.8, which is really the first section in chapter 5. Antiderivatives by hand, differential equations, which are just like antiderivatives, initial value problems where you find the plus C, and slope fields. Be able to do all of those. They're pretty simple, pretty mechanical, but they're the foundation for what we do in Chapter 5. That's like the arithmetic for Chapter 5. If you have any questions or comments, come see me. Other than that, thanks guys.